Okay, folks, welcome to Module 3 of Computer Graphics. Glad to be back with you. And we're going to resume where we left off, continuing on our ray tracer. So let's go ahead and dive in. Okay, so just some fun warm-ups to get us back in ray tracing mode. One of my favorite websites is by this gentleman, Fabian Sangard, who writes a nice blog, and he's come up with quite a few cool algorithms and discussions on just different computer graphics things. But one of the fun things that he posted, relatively recently, or that I stumbled upon, was this sort of ray tracer in, building an entire ray tracer in just this amount of lines of code. Now, it's very ugly code. It's very hard to read, but it just kind of goes to show some of the cool stuff you can do with ray tracing in just a really small amount of code, right? Ray tracing is more of a thinking about the algorithm and how to generate a cool shape as opposed to thousands and thousands of lines of code, which is why it's such a powerful and cool technique. So this is just sort of a for fun ray tracer, the postcard size ray tracer here. If you want to actually try it out and run this code, I think it's kind of fun. The original idea actually comes from this gentleman, Paul Heckbert, who put a business card. He's a big sort of graphics guy, but he put this code on the back of his business card. It's kind of a fun idea that he would have a complete ray tracer here. So quite an original idea. I like it. There. Some more fun with ray tracing as well. I stumbled upon this recently from a friend on Twitter actually posted about this, and from the same gentleman, Paul Heckbert, on a ray tracer that simulates Jello. So this was published in 1987. So this is kind of the state of the art back then, being able to generate some of these scenes. But also, the interesting or why it's complex or impressive is these sort of curves at the time that were being displayed, this translucent material. There are shadows here. We call these soft shadows in the sense that they're not just darkening all the pixels. So this is pretty impressive at its time. There's even some specular highlighting, which we'll learn about. So quite a bit going on even in this little scene, and kind of funny that this is what some of their folks at Pixar and the Dessert Foods division were publishing at a top conference. Okay, so last lecture, what we were talking about was this idea of ray tracing, working through the Peter Shirley book. We're going to finish that this week. That's why this is going to be our next lab to finish the book. I think some folks actually did, so you're ahead of the game. And it's quite a bit of programming in a sense of you getting used to C and C++. So there's no assignment this week. It's just finishing the lab and getting up to speed on your C and C++ as we learn ray tracing. So the basic idea is this is our first technique, our first rendering technique for drawing computer graphics. We're drawing sort of one frame or one image at a time by casting rays from our camera and determining if they intersect with any object, and then returning a pixel color of that object to the screen. Okay. We're going to learn this is a different approach than rasterization, which is where we're drawing the closest pixel of an object where we know that object exists because we're in control of drawing it. So it's a little bit of a different approach, but again, roughly speaking, you can generate the same graphical scene, but they have different purposes. Ray tracing, we'll see, can typically get us much further when it comes to computing light and shadows and some of these other things. So these were some of the benefits of ray tracing, this idea that we can really simulate physical lighting in the sense of we can understand how light bounces around more accurately. Okay, so by the end of the last class, you should have a scene like this with 3 spheres. That was the goal for your lab 2, which you'll submit anytime today or anywhere on Earth where it is still Friday. So this was the goal. Okay, so to get the next lab, go ahead and do a git pull. That's been uploaded to your repositories online. If for some reason you don't have it, just send me a Piazza message as soon as possible, and I'll make sure it gets uploaded. But otherwise, you may proceed there. And again, today's goal is going to be to continue the development of our ray tracers. So this will be a little bit of a weird lecture in the sense that I'm just going to jump into the Peter Shirley book because that's what I want you working on. Something that's new about this course that I'm excited about is we're actually starting with the ray tracer, which I think is pretty cool. So normally we would do this at the end of the semester, and it's sort of an optional activity, but you guys are going to be ahead of the game, and we're going to do these ray tracers properly from the start of the class and actually finish them, which is great. Okay, so ray tracing in one weekend is going to be continued, but I want to talk a little bit more about the math before we just dive back into the book. Before we're looking at chapter 7, there was this concept that came up in chapter 6 about normals. We're talking about how to shade the surface of this sphere here, or you guys are drawing circles, and then there'll be spheres once we shade them in. But we need something called the normal. So again, depending on when you've taken your last math course, the term normal and vector, these are some new terms. So we learned a little bit about vectors, it's a mathematical concept, in 2D or 3D space. It's something that contains a magnitude and a direction, okay? So we learned a little bit about those normals, those vectors, but a normal vector is a vector that's perpendicular to a plane. So this diagram here in the bottom right corner most clearly shows that. So here's a plane, and this normal is perpendicular. Sometimes we'll use the word orthogonal, which means the same thing, but it's perpendicular. It's coming straight up at a 90-degree angle from this plane. If I tilt this plane, I would also tilt this vector to the side such that it would also be perpendicular to it, okay? Here's another visualization. Again, I like to think of this as a porcupine or a hedgehog with spikes coming off of it. But all of these little spikes here, these white arrows here, are vectors that are perpendicular to this surface, okay? They're exactly at a 90-degree angle from this surface, okay? So that's the normal. And we can compute the, or we can make use of this normal vector to help us in lighting. And that's what was going on when we were shading this object. We were computing the dot product of this normal vector, again, so these white little spikes here are the normal vectors, against some light source. And then based off of that value, some value between 0 and 1, we figured out how much to actually light up this object, okay? So I introduced a new term. You probably read it in the book, but again, this idea of a dot product I want to introduce. Okay, so some more sort of handy vector math, the dot product and the cross product. These are two mathematical concepts that are going to keep coming up over and over and over again, so I want to introduce them now as you're using them. Okay, so the dot product first, just an example of where it's used, again, vectors in games. The dot product's really used to find the angle between two vectors. So here's two vectors. If you've ever played like a racing game, here's an example. I'll give some more if you haven't, but here's a little booster pad. And if you drive over it, here's where it's going to sort of boost you and make your car go faster, or your kart. And then here's the angle that you're approaching this booster here. So depending on what angle you hit this booster, if you hit it right on here, you're going to boost really fast. If you hit it at a, not in a parallel or 0-degree angle, then you'll get boosted proportional to that angle that you're coming in. Okay, right? So if you just hit the little corner here, you'll just get boosted a little bit. Okay, so that's an example of why we might want to compute the angle between these two vectors to give us sort of a more realistic effect here in a game. Okay, we're going to also, we're primarily going to be talking about using the normal to figure out the shading of a surface. So that'll be another primary use. Okay, so how do we compute the angle using this thing called dot product? Again, dot product tells us the angle between two vectors. And if we take the product of vector A and vector B and the result is 1, that means we're moving parallel. Vector A and vector B have the same direction. Their magnitude might be different, it doesn't really matter, but the direction is the same. They're parallel, or we say they're collinear. They're moving in the same direction. A product of 0 means both vectors are perpendicular to each other. So vector b, if I dot it with vector a here and I get a product of 0, that means they're perpendicular. So this is good. So we can use the dot product to figure out if b is perpendicular to a, right? A dotted with b will give us 0. And a product of negative 1, excuse me, means that they're moving in complete opposite directions. So b is moving, in one direction opposite of a. So we'll get a negative 1 here. Okay, so that's the range when we're computing the dot product, -1 to 1. Okay, so how do we actually compute the dot product? Vector A and vector B dotted, that's usually how we say it, or dot product of A and B. We could just say A dotted B, yields a scalar value. It's between -1 and 1. And we get that by multiplying and adding together the components. Okay, so A dotted B, we take the x component of A and the x component of B, multiply them and add the y components of A and B, and then add them to the z components of A times B, and then I get some scalar value. Okay, and then typically we normalize that so it falls between -1 and 1. The equivalent way to compute a dot product, so a dot b, can also be computed by taking the magnitude. Remember, that's what the bars are. So the magnitude or the length of this vector. We learned about that last lecture. It's the components of computing this magnitude, the square root of a of x squared plus a of y squared plus a of z squared. That square root gives you the magnitude. Multiplied by the magnitude of b times the cosine of theta equivalently computes the dot product, okay, if you know what angle they're coming from, okay? Okay, so when the magnitudes of our vector are 1, that is, so when we have them normalized, then we can retrieve the angle between the two vectors in a convenient way, right? So if they're just, again, just taking this equation, if the length of A and B are 1, that means we've normalized them ahead of time. Again, so it just means this gives us a unit vector. So a unit vector means all of its components squared and added together will return 1 times this cosine. This makes it very easy for us to get the angle. So again, that's why we like to sort of normalize or work with normal vectors, because when we do, with unit vectors. And so we can easily compute things like the dot product. Again, so if A equals 1 and B equals 1, that's just 1 times 1 times the cosine of theta. And then we can figure out the angle between these two vectors, A dotted B, by doing the arc cosine of A dotted with B. And then this will tell us the angle between them, okay? So in our Mario Kart example, if the angle is bigger, we boost less. If the angle is really small, we boost more because there's less of an angle between these two vectors. Again, so if it's 0, they're collinear or moving in the same direction. If it's negative, then boost in the opposite direction. Okay. Okay, so that's a little bit about the math. It can be helpful to also visualize how the dot product is computed. Again, each component's x and y is sort of abstracted out here. So the x of the red arrow is shown here, and the x of the blue vector here, b, is shown. So if I sort of take whatever that length is, so here's the length of this one, it's this which matches here, and the length along the x-axis here, which matches here, and the length of y here, y, and the length of y of b here is here. Excuse me, so these all match here. This is how you can compute the dot product, okay? Now there is sort of, this hidden computation of ay times bx. Oh, that just equals 0 here because they're perpendicular, and ax dotted with by equals 0 here. So normally we don't talk about these, so I like this visualization because it's actually showing that. And you'll see what we're building towards from the dot product here in a moment. But again, here's just the visualization of each of the components, okay? So again, dot product, another use case, again, just remembering how it's used. Dot product tells us the angle between two vectors. Again, if we get that angle of, if we take the dot product and we get a 1 on this side of the equation, that means they're moving in the same direction. So the angle between them is 0 here. If the dot product is 0, that means they're at perpendicular to each other. So the cosine of 90 means 0. So they are perpendicular, okay? If the cosine of the angle is greater than 0, that means they're moving in the same direction. So the angle must be less than 90 degrees, right? They're just moving somewhere in this direction. Say, this gentleman's walking forward and this guy is also walking forward. If it's less than 0, that means they're moving in the opposite direction. So the angle has to be greater than 90. So, I'm moving, slightly this way back while one of these gentlemen is moving slightly forward, okay? Another practical usage, again, is in this sort of gaming scenarios, it might be useful to tell if an enemy is in front of us or behind us or within sight on something like a radar, or for our artificial intelligence, these characters here, if they're moving, or looking towards us, we can use the dot product to figure that out. Or if they're looking away from us, then they can't see us in their line of sight. Okay. So some products of dot product. Again, your takeaway for now at this first look, just know how to compute it and start internalizing some of these ideas of if we're moving in the same direction or what the angle is for the dot product. Okay. So some products, or some properties of the dot product are that A dotted with B is the same as B dotted with A, because we're just using multiplication and addition. Those are commutative properties, so you can do these in any order. You don't have to worry about that. And then the dot product is distributive with addition. So A dotted with the accumulation of B plus C is equal to A dotted with B plus A dotted with C, right? So it can distribute this dot product. Okay, so here it is again, the main usage that we're concerned with, at least in our real-time ray tracers, on dot product usage and lighting. Just again, showing the vectors, trying to give you some idea of what's going on. At least through chapter 6 in the book, you don't really have this idea of a light source. It's the camera or where you're looking at it. But you have some light vector, it's coming in at some direction and it hits a surface. And from this surface, you learned how to compute the normal vector. That was the diagram sort of presented in chapter 6 that we started with. And then if you take the dot product between where that normal vector is and where a light source is, or currently your camera, that angle tells you how much to light up this surface. Okay, so if the angle, and these are, I guess, moving in opposite directions, but if the angle's, something negative, then it's moving the opposite direction, so we shouldn't apply any light here. Okay, if it's right on, this angle is very small, that means the light's hitting very directly to this point here, so we should light it up more. Okay, if the angle is really big, that means maybe somewhere up here, that means the light's not really directly hitting it, but we should light it up a little bit. Okay, proportional to what our dot product is. Okay, so related to, or somewhat related to the dot product, is another handy tool that we're going to use in vectors called the cross product. And then this is useful for actually figuring out a vector that's perpendicular to two other vectors. Okay, so the cross product, and here it is sort of visualized, is a vector that's perpendicular to two other vectors. So we have vector A here, vector B, and then this one's perpendicular to A and B. So you can see the right angle symbols here, okay? And again, we like or want to use this cross product to give us a vector that's perpendicular, because if we look again back at our normals, let me go to my favorite visualization of it, with the hedgehog sphere. Oops, here. This is perpendicular, right? So I can take one of these sides here, that's a vector, and then one of these sides here, we have two vectors, and then compute the cross product and then get this normal that's perpendicular. Okay, just pick one of the edges of our quadrilaterals here. Or if we have a triangle, it doesn't matter, we just need two sides. Okay, and that gives us the cross product. Okay, the actual computation of the cross product looks like this, where we have a vector u. It's got an x, y, and z component, and a vector v. It's got an x, y, and a z component. And then when we multiply them, we'll get a new x component here, a new y component here, and a new z component here. Now, how I compute it, you don't have to memorize it for this course, but I take the u2, which is here, and v3, which is here, and I subtract it from u3 and v2. And you'll notice a little pattern. There's a nice video that shows this a little bit better, but since I'm computing the x component here, I'm not using u1 or v1, which fall in the x component spots here, so they're not being used here. And then similarly here, I'm computing the y component, so I'm going to use the third component and the first component, but not the second one here, okay? And that's the cross product. So you don't have to memorize this, but you do have to compute it properly by looking at a formula like this to see how you can get a new vector x, y, and z that's perpendicular to a and b. Okay, so cross product, though, we have to be a little bit careful. Its properties, it's not commutative. That means a crossed with b is not equal to b crossed with a. So the order really does matter here. It is something that's called anti-commutative, where a cross b is equal to negative b cross a. We won't need to really think about that too much, but just keep in mind that the order matters here. Okay, so again, on the normal vector, just keep in mind a normal vector is a vector that's perpendicular to a surface. Okay, and it's heavily used in things like lighting calculations, which we'll need. So again, here's just that perpendicular vector here to two surfaces. Okay. Here's an example, again, just showing some more examples of the normal vector and dot product being used in something called, it's a technique called bump mapping. So on the left side of this slide, you'll see what's called a bump map. Okay, it has more texture, it's more interesting to look at here, as opposed to on the right side, which is very flat. So on this side, we're actually on each of the pixels here, figuring out where the normal vector is, and then from a light source, computing a dot product with that normal vector here. So we've computed the cross product at each of these little surfaces here, and then we compute the dot product from our light source, and it'll allow us to lighten or darken each pixel here and give us this appearance of a sort of bumpy figure. Okay, so this is something we're actually going to implement in OpenGL later. You can also implement this in your ray tracers if you like, but just an idea of what the power of these two very simple tools that we just learned, dot product and cross product, can give us a nice visual, like what's on the left versus if we don't know our math, we get what's on the right here. So kind of cool what a little bit of math can get us. Just two other or a few other small topics on vectors before we move back to the ray tracer, talking about tessellation. The other things we can do with vectors, occasionally it's handy to be able to compute the midpoint. So if I have a vector, so going from O of A and O of B, and I want to compute this midpoint here, I just take 1/2 of vector O of A plus vector O of B, and that lands me right in the middle here of these two points here. Okay, so that's handy when you want to compute the midpoint of something. So here's an example. It's called the Sierpinski triangle, where we want to subdivide this triangle into smaller triangles. So it looks like this. And basically, I'm taking the midpoint of each of these points at every edge in this triangle here. So I get the midpoint, I can do this again and again, and so on. Having more subdivisions can be useful because it gives us more surfaces. And if we have more surfaces, these small triangles, we can compute the cross product of these and get a normal vector. And then we can get more accurate lighting by being able to, per each of these triangles, compute the normals versus just one, lighting this entire surface up with just one value. That's the same. We can do this on a smaller level. So that's a little bit of the motivation. Again, if you don't understand that, just know that we can break a triangle down into smaller pieces. It's called subdivision, and it's a powerful technique for adding more detail to our models. Right? This has more detail to a 2D or a 3D shape. Okay, vectors in physics, sometimes it's useful to be able to compute the center of mass of an object. So here's the center of mass where I just take O of A, so wherever my, from this point here, and I compute O to A, O to B, O to C, and then I take 1/3 of that, and that gives me the center of mass from this point here. Okay, so here's the actual vectors being drawn out here. The center of mass is here. Okay, so just to note that vectors and graphics will be 2D, 3D, or 4D in other fields. There may be many other dimensions, and you can apply and modify the formulas as needed. Now, something we might revisit a little later, I might require you to watch, but I think is one of the best explanations of just using vectors and to reinforce some of the vector math that we've been doing. It's this talk by a gentleman, Zaiba, who's actually local to Boston, and I've seen speak a few times, has this talk called A Little Math for Your Big Ideas, and he builds a whole sort of physics simulation in about 26 minutes. So if you do have a few extra minutes during lunch or something and want to play this at 1.5 times speed, it re-explains vectors, center of mass, and shows how it's applied. This stuff isn't particularly complex, when you compare it to like learning various, multidimensional calculus or something. But just the math that we've learned is enough to build this kind of water simulation, which is pretty cool. So do take a look at that if you want some more examples. Okay, so with that though, give yourself a break if you haven't already, and we'll continue with our ray tracer. Okay, and if you're powering through or rejoining, let's get continued with the ray tracer. So after last week's lab, you should have successfully worked through the first 6 chapters of the Ray Tracing in 1 Weekend book. Okay, for the remaining of the lecture, I'm going to help us walk through some of the important parts, I think, chapter 7 through 13. Again, this is in part an exercise for you to work through and make sure you get familiar with the math and some of the graphics terms. We'll revisit them again in OpenGL, but this is our first take at it. Okay, so I want to walk us through some of the important things here in the book here. Okay, so moving through chapter 7 and beyond here, it starts off with where we left off here. Is some different ideas. Let me start from chapter 6 on using the surface normals and being able to draw multiple objects. Okay, so this is largely what we've covered today. Okay, here's the picture showing the surface normals. There's a little idea here that you're getting these interesting shades of a greenish tint, a reddish tint, and a bluish tint, because that's if a vector, which is something that contains 3 components, x, y, and z, those values correspond to the R, G, and B values for red, green, and blue. So that's why you're getting the various tints on your sphere. Okay. Then he goes through and simplifies a little bit the intersection code. So you're figuring out if you've actually hit an object. Shirley then starts to abstract and make a hittable class. So you can just determine if what the type of the object is and implement these functions to determine if it was hit. He talks about the front versus the back face as well, which is the idea that when you cast a ray, if it goes through an object, it'll go through one direction and out through the other end of that shape. Right, so if you had a balloon and shot a laser through it or a dart or something, it would come in one side and out the other, and that's what this discussion's about. To tell us, if we're inside the actual shape, we don't really care too much about lighting it up, but on the outside, what the viewer will see, so that's what we want to light up. Okay, so then just some other ideas about keeping track of objects that are hit, some new C++ features, this idea of using pointers, okay, which a pointer is something that holds an address. and then some other utility functions here. Okay, and he wraps us up with our sphere here. And then your goal is to draw 2 more. So chapter 7 talks about this idea of anti-aliasing. Okay, so the idea is when you draw something on a screen here with anti-aliasing, you see it's not a perfect sphere. Mathematically, we know it is, but we only have a discrete amount of pixels on our screen. So if I zoom in here, this is as much as I can zoom in on the browser, you'll see there's like these little stair steps, these discrete steps that are taken. The idea is we see that's something called aliasing in graphics. We want a smooth circle shape, right? This is distracting. We can notice it. It doesn't look realistic, right? Because when we view things in the real world, things aren't jagged like that. So what Shirley describes it is that we can generate a pixel using multiple samples. Okay, and this idea of sampling around nearby pixels to see if we're close to hitting them or close to hitting our shape, we can fill in with sort of a subpixel, or if you want to call it that, shade in the nearby pixels in approximate color. And if we do that approximation around our sphere, all of a sudden you notice and it looks more spherical, right? As I zoom out, this shape looks more spherical. It's harder to tell and see those stair steps, okay? So you can do multiple levels of anti-aliasing. He's going to give you at least one, and it'll sort of smooth out this circle. Again, if you zoom in really close, you'll see it gets sort of pixelated is the term we use. But when you zoom out, this looks pretty good. Again, we get a better approximation of that sphere. Okay, so there's the zooming out. Okay. Chapter 8 then begins the idea of, well, we have these colors here, and we've chosen colors for our spheres, but we actually want materials. We want to simulate what things look like in real life. So he's going to start off with a diffuse material. So he describes them as materials that don't emit light, but they take the color of their surroundings, right? So we could just say something is red or a fixed color. He talks about sending some more rays, but here's a first sort of diffuse color material here, okay? So it gives us a sort of grainy color. It gives us some idea of, the light kind of hits this object and scatters, and it's not necessarily uniformly lit. So this looks pretty interesting to us, okay? But he wants to get more accurate color. So he's using this thing called gamma correction to give us a lighter sphere, and this all of a sudden looks a little bit better as well. Then he's going to fix the shadows, and then we end with this sphere here. So this looks pretty good here. The lighting's pretty good. It doesn't have as much noise. If you look back, I think he gives it the term noise acne, which I don't know if that's a graphics term that he made up or what, but it looks a little bit better than this, right? We're getting some darkness. It does look kind of pixelated. So the color has been corrected a little bit, and it's looking better, okay? And there's some alternations that he plays around with. But then the rest of the book moves into some cool stuff on materials. So, it's enough if we have that sort of diffuse, sort of fixed color material, but we want something, all objects, in a sense, can reflect light or scatter it in a way. So like a metallic object, he then models, okay? So he goes through and talks about how to build a sort of reflective object. So this sphere here, if it's totally metallic, when I cast a ray towards it, we bounce the light once and then see what that sort of reflected pixel gives us, okay, right? So I have a vector coming in, it hits the surface, and then it bounces, and if it gets a red pixel, then we go back and color where we bounced from red, okay? And that's essentially how we model a reflection. Okay, then he says, yeah, we can make things kind of fuzzy by adding a little bit of noise and scattering our rays, and that gives us something like this, sort of a frosted effect, if you've ever seen like a frosted window. When light scatters, in a different direction. You can also think of that like refraction. So if you've ever been in a pool or underwater and looked up, the light kind of bends in the water, so it looks a little bit strange. So that's this idea here. And he actually goes into the refraction here and gives us Snell's law, which describes refraction. And we get some shape like this. So you can see that, light's sort of refracting here and bending. Okay. Okay, so this is refraction. It gives us a hollow glass sphere here, some interesting materials. So your goal is going to be to, implement at least 2 of these materials. I would, again, recommend just walking through all of it. Shirley's walking through and giving you the code. For the most part, this will give you some ideas of programming in C++ as well to keep us warming up there. Chapter 11, he gives us a positionable camera. So now we can actually move around in our scene. Okay, so he describes a camera, the components of it. We'll look at it in OpenGL more in depth what these look from and look at camera, but basically you can model a camera in the world here. That's this red thing, and you want to have a direction where you're looking from, so that's sort of your position in 3D space, and then where you're looking towards, right? So if you turn your head somewhere in the world, where your eyes are pointing, that's where you're sort of looking at. You're focusing in on an actual position here in space, an X, Y, and Z position. Okay, and then the camera's modeled. Someone asked about this in Piazza. So you have your direction you're looking from, where up is in the world. So for us humans, most of the time it's 0, 1, 0. The y-axis is pointing up. So that's just a vector telling us where up is in the world. In space, it might be different, in outer space. But this is the idea of modeling our camera. So it builds a little camera that we can position around the scenes. We have our spheres in 3D space, so you can actually move this around. Okay, and I believe the last topic he talks about is blurring, and this idea of how a camera sort of works, where you have a film, a lens, and where it focuses on. And then anything that's outside of this focus can be blurred, or we can sort of scatter the rays a little bit. Okay, so if we're focused here, we can blur what's around us. Okay. Finally, and you have total creativity in your actual assignment for this, you can create as many spheres as you want in whatever materials. Try to show off at least 2. Okay, and this is sort of the classic image that's generated from the book. It's the cover photo, and it looks pretty darn cool, if I might say. We've got reflections, we've got sort of glass spheres, we've got the dielectric materials. So pretty cool. So your goal is to, this might be a little bit more programming intensive week as you finish this up, is to work through the rest of this text. So because you have the code and sort of an option to finish it, I think it's reasonable. But again, to work through this. As you see things that you don't understand, like if you don't understand what a class is, what the auto keyword means, what a shared pointer is, please post those things on Piazza. Please do a quick Google search and then post on Piazza, because those are some of the other reasons I'm having us go through this text to get us warmed up on C++. We won't need more than what's given, but since this is your first look at things, I want you to understand what's virtual mean. Well, I'll just tell you, virtual means this function here can be overridden by something that's inherited. Okay, so this material, for example, might have a virtual function that we can override and implement in dielectric. Okay, so if that sounds weird, just let me know. Okay, and we will take care of it on Piazza. Okay, so that's the Shirley book. We can work through it. Try to generate, you can be creative, but something like the final image shown in the book, and then you're done with your ray tracer. Okay, so that's a quick walkthrough of that. I want to pick us back up in the lecture, finished with some, more ray tracing fundamentals and new hardware. This is just sort of a future look at things. When we talk about ray tracing, it's what's known as an embarrassingly parallel computation. The work that you're doing right in the core of your ray tracers is casting one ray per pixel. And that's something that could be done in parallel. You could cast all of those, if you had enough computers or enough cores on your machine to do them in parallel, right? Because they're sort of independent of each other. So that's why we say it's embarrassingly parallel. So if you have one thread, on your machine casting a ray at a time, again, that's happening independent of any other task that happens. You can do this in parallel. So what folks have thought about as they've been doing ray tracing for all these years, that said, hey, why don't we just have specialized hardware that supports this? So there's something new from NVIDIA. And by new, I mean like this year new, this year and last year, but something called the Turing architecture has been developing, and it has specific cores on it, or at least specific hardware that supports this task of ray tracing, okay, where its job is to cast rays. And so there's a little bit, if you want to read about that. But again, ray tracing cores, RT cores, are designed to do specific tasks like ray triangle intersection. Okay, we're doing ray sphere intersection. We're going to find out in 3D graphics things are all modeled as triangles, but we can do this ray tracing task. So here's an idea of, here's a bunny here. It's called the Stanford bunny. And you'll see little boxes around the areas where there are pieces of the bunny. So there's no piece of the bunny here, so there's no sort of box. So we can just cast rays through anywhere where these boxes are, right? This gives us a smaller space, and determine if an intersection occurred, because we think there might be some geometry here. If it does, then we shade it in, okay? So this is the idea here. This bunny has what we call a bounding box around it. So we only need to shoot rays from our camera to where these boxes fill space, okay? This has a special data structure that's known as a ray bounding volume hierarchy. BVH is what it's abbreviated. And you can see this in the ray tracing video. Okay, it's a cool algorithm, this bounding volume hierarchy. I believe the next Peter Shirley book will have you implement it, or maybe by the third, and this is a good candidate for final project if you want to take the ray tracer further. But it's a way to divide your scene up into a tree-like data structure. Again, sort of thinking about your object as a hierarchy, so A, B, and C. If part B of the scene, so this sort of bounding box, only contains these objects, then you only have to worry about these particular objects interacting or overlapping each other, or so on. Okay, so you can sort of combine this bounding volume hierarchy with some other tree-like data structures to get optimizations. Not something we have to worry about right now, but just know that there's different optimizations for improving ray tracing. Okay, the other things we want to keep track of or sort of keep in mind in the ray tracing world is the increasing GPU memory, so that we can do this ray tracing task on our GPUs or take advantage of these ray tracing cores to do some of the work for us. Okay, so if we sort of see over time on the x-axis the different NVIDIA products that are released, and on the y-axis here how much gigabytes of memory we have, we can see it's going up pretty darn fast here with how much memory we have. And some of these, more special purpose architectures here are really improving how much memory we have. If we have more memory on our GPUs, we can do, hold more data there, hold more interesting data structures, and get prettier images. Okay. So just from a hardware perspective, we're going to start looking at next week the rasterization process, how things work, and we've looked at ray tracing. But the general idea is both have a pipeline that's followed. So let's look at ray tracing since that's what we've talked about. We generate a ray, And then on the hardware, so this is on the GPU end, if you want to do GPU ray tracing, it's sort of scheduled that, hey, this ray is ready to go. And then you perform the traversal of that ray, test for intersection, and then you can schedule it again, and then perhaps shade in a portion, and that ray might bounce once it gets scheduled again, traverse, intersect, schedule, and bounce around, right? You have that sort of recursion. Rasterization, on the other hand, is much more linear, where you're gonna issue, hey, I want to draw something, say a triangle. You say, hey, queue up, schedule that drawing of the triangle, start shading it in, start filling in the pixels, fill in the pixels different values, and then show the image. Okay, ray tracing again has this sort of recursive nature here, where you might do things many times. You might bounce the rays 5 times, through this cycle. Okay, just in a little bit more depth is this video here explaining modern ray tracing hardware. Not something at all you need to understand at this point, but just know that the hardware is trying to take care of some of this for us by testing intersections, testing if we hit anything, accelerating the traversal of that ray traveling. Those are just some of the things going on in the hardware. So folks asked about, so I just want to explain a little bit more about what's going on in the hardware. I think, again, this series, I'll just go to the videos. I won't play it. The Ray Tracing Essentials is really good and worth a watch. So those will be included on your sort of pre-course readings. So some of this, by the time you're watching the lecture, might be redundant, but this is a great series for that. Okay, so what next for you to do? Well, you want to finish off your lab, but we're actually going to start moving on to rasterization and the next stuff. But you might love this ray tracing stuff, and again, this is an option for your final project. You can look at ray tracing the next week, another excellent free book, and it will help you generate scenes like that. And then ray tracing the rest of your life. You'll see how to generate some of these scenes. So I think it's pretty cool. There's another great book here, Physically Based Rendering. Spoiler alert, this will probably be a pre-class warm-up, but this is the only book that's been sort of nominated for an Academy Award. So kind of fun to know that. But this is an excellent book, also free. You can click on the link here. And it's probably something you can read after these 2 books and really get a lot out of it. Okay. So again, a few folks asked about real-time ray tracing. I think it's worth taking more look at to get excited about graphics. Just some examples of some projects. This is all real-time stuff shown here. This is from 2 years ago, so it's kind of old even by today's standards, but a real-time game here. And then here's another talk on just ray tracing explained if you want to keep hearing some more explanations from different perspectives. Okay. All right, so with that, make sure to complete your in-class activity. That's what's on the agenda, so just a few questions there. Make sure you get that in by next week. Here's your break. And then the lab, as mentioned, is just going through, again, the Peter Shirley book here, the next chapter 7 through 13. If you have questions, again, on any of the C++ stuff, please let me know. We're going to try to, get as familiar as we can these first few weeks with that. And then we'll move on to rasterization and modern OpenGL in this next week, which is very exciting stuff to be starting on. All right. So with that, we'll touch base shortly. I'll see you folks in office hours, and we'll touch soon. Or we'll be in touch soon.